Hi, my name is Michael Wang, and I'm going to be talking to you today about radio access technology selection in heterogeneous networks. This project, as Wang said, is done in collaboration with Intel Labs as a part of their Higher, Denser, Wilder 5th Generation Wireless Networks program. And we are currently collaborating with them to explore how our results, which I'll present in this talk, may be incorporated into future 3GPP standards. So heterogeneity of wireless network architectures is increasingly becoming an important part of current and next generation wireless networks. At the same time, mobile devices are increasingly equipped with multiple radio access technologies that allow them to choose between and connect to different access networks. So the coexistence of a variety of these different network architectures, such as 2.5G, 3G, 4G, Wi-Fi, and things such as femtocells and distributed antenna networks, and the ability of users to choose between these different access networks leads us to the following question. With all these different choices of RATs, how should a user select the best access network at any given time? This problem is actually much harder than it originally appears. For example, you can think of this using an analogy that we like to talk about called the highway analogy, where we view users switching RATs, or access networks, in order to gain a better throughput as cars on a highway trying to switch lanes to get a better speed. In a scenario with a lot of cars, basically in a scenario with a lot of cars and unrestricted switching, where users are allowed to switch lanes whenever they want, this can lead to increased congestion and an overall decrease in per user throughput. This is also true of users switching access networks to get a better throughput. This is clearly not good for users who would like to get a higher throughput for throughput-intensive applications such as video streaming or real-time gaming. So there exists a need for some sort of radio access technology selection algorithm to sort of govern the switching behavior for users. And here's a common example of radio access technology selection algorithm is the following, which many of you who have Android or iPhones may be familiar with. The algorithm goes as follows. If you see Wi-Fi, connect to Wi-Fi. If you don't see Wi-Fi, then stay on your 3G, 4G. Clearly, this is not the best radio access technology selection algorithm out there, because it clearly falls prey to something we call the tragedy of the commons, where as more and more users are shunted by service providers onto Wi-Fi, and the number of users on the Wi-Fi network increases beyond 10, we see an observable decrease in per user throughput. Again, this is really bad for applications that require high bandwidth, or high throughput, such as video streaming and real-time gaming. So before we get into the details of our work, we first need to discuss the way a potential algorithm for RAT selection should actually function in a heterogeneous environment. So there's been quite a bit of prior work done in the past couple of years in the field of centralized coordination by Ibrahim and Yi. The nice property about centralized coordination is by having one center node govern all the users in a system, we're able to lead the entire system to a state called Pareto optimal, where no user can increase their throughput without harming someone else. So this is something that is very desirable. However, centralized coordination is not very realistic, both for technical concerns and economic concerns. So technical concerns are, for example, this type of centralized control does not scale well with the number of users. For example, you can imagine a single controller for a small geographical area, say New York City, with the millions and millions of users within that single location. In order for this to work, the centralized control node must receive completely accurate information from every single user describing what RATs they can possibly connect to. And it must receive this information, run the calculations, and assign which user should connect to which RAT really quickly. And you can see that this is not very easy to do. Even more so, there are economic concerns. For example, if I'm AT&T, why should I allow a Verizon customer who isn't paying me, who isn't subscribed to me, to use my network? I have no financial incentive to do so. And even in the case where, let's say, a bunch of service providers get together and say, okay, let's implement centralized coordination, the question still remains, which third party has to administer this centralized coordination node? And what exact algorithm should it run? So our contribution is basically saying, instead of aiming for an unrealistic centralized coordination scheme, let's aim for a more realistic distributed algorithm that can be implemented in today's modern wireless networks. Although we won't achieve the nice Pareto optimal property of centralized coordination, what we'll be able to show later on in this presentation is that we can achieve almost Pareto optimal solutions, and we can bound this gap, this difference between centralized and fully distributed. So we define the rat selection game as a non-cooperative game, where each user's goal is to maximize their own individual throughput. So users are greedy. And we describe the set of players as the set of users who want to obtain a better throughput. And we call this strategy profile sigma as basically the exact associations of each user to the rat. So sigma 1 basically is user 1 and its choice of access network, and so on and so forth. We also utilize the concept of the Nash equilibrium, which basically says a set of users and their associations is at a Nash equilibrium if no user has an incentive to switch rats, given everyone else staying the same. So let's describe the network model we actually use in our work. So we assume there's a heterogeneous wireless environment where users have access to a wide variety of different access networks, such as Wi-Fi, 3G, and LTE. Each user has access to a user-specific set of rats. For example, one user can access, say, 2 Wi-Fis, while another could access Wi-Fi, 3G, and maybe an LTE base station. We also model multiple base stations as multiple rats. So for example, if both 3G base stations are run by, say, AT&T's cellular network, we model them as distinct base stations to explicitly model which base station a user connects to. We also assume that there's no traffic splitting for simplicity, so each user can connect to at most 1 rat at a time. And finally, again, users are greedy. They would prefer more throughput to less. You can't do worse with more throughput. So it's clear that if there's multiple users on a given rat, there must be some sort of throughput sharing going on behind the scenes. And here are the 2 models we use on our work to approximate the behavior of Wi-Fi and 3G. So in the class 1 throughput model, the achieved throughput of user I on rat k, omega ik, is basically a function of all the physical layer rates of the users on that network. So something immediately apparent is that in class 1 models, each user on rat k achieves the same throughput because the function is exactly the same and the inputs are exactly the same. Examples of this could be throughput fair models or the distributed coordination function DCF in 802.11n. And the example below is basically round robin, where each user receives time to transmit proportional to 1 over its physical layer rate. So we can sort of view that as Wi-Fi. In class 2 throughput models, the achieved throughput of the user I on rat k is a function of that user's own physical layer rate multiplied by a function of the rat that only depends on the number of users on that rat, not their individual rates. So immediately we can see that class 2 allows users to have different rates on the same rat. Examples of this could be time fair or proportional fair scheduling on 3G. And the most common example could be basically time division, where if there are 10 users on the network, each user gets 1/10 of the time to transmit at their rate. So our algorithm for distributed rat selection is as follows, which we'll be able to show some simulation results later. So in order for a user to switch from one radio access technology or access network K to a new access network K prime, the following 3 things must hold. First, a user must expect to gain at least eta times its current throughput. So eta is a tuning knob that we will talk about later, the switching threshold eta. You must expect to gain at least that much on the rat you're going to switch to. And it must hold for at least capital T consecutive time steps. So basically, we need to be relatively sure that if we do switch, we will gain more throughput. We also introduce a parameter for hysteresis, H, which basically is a memory of our throughput on the other class. This helps us attain convergence, as we'll see in the next couple of slides, and prevent interclass oscillations where users might jump between class 1 and class 2 over and over. And finally, we have a randomization parameter P that is similar to exponential binary backoff that allows us to prevent, or at least mitigate, a large number of simultaneous switches, which may cause users to oscillate as well. So here are some, now we move on to several theorems that we've been able to derive, and these are actually not specific to the distributed algorithm. These are true for all general algorithms. So what's really surprising is we've been able to show that for class 1 and class 2, basically only Wi-Fi or only 3G, these rat selection games always converge to a Nash equilibrium, which tells us that this is extremely applicable to, this is a good substitute for a centralized algorithm because we can actually talk about the entire system coming to a single convergent state. However, if we look at the case where we have mixed classes, for example, users can connect to class 1 and class 2, such as connecting to Wi-Fi and 3G at the same time, these do not always converge. However, using the hysteresis parameter that we introduced on the previous slide, to prevent oscillation, we can show that this does converge to a Nash equilibrium. Again, these are really important theorems because they tell us that we can actually use fully distributed algorithms in place of a centralized control scheme. So now that we've been able to show that these things actually converge, let's take a look at how good are these convergence points compared to the centralized control that we're looking at. So we do this by talking in terms of the average Pareto efficiency gain, which is basically the average per user throughput gain between your current distributed Nash equilibrium and a theoretical centralized Pareto optimal state. So basically, how much would you gain from switching from distributed to centralized? And we've been able to show that for class 1 rat selection games, some Nash equilibrium are actually Pareto optimal. And this is very interesting to find out. However, we've also been able to see that the average Pareto efficiency gain can become unbounded as the ratio of maximum to minimum physical layer rates goes to infinity. Unfortunately, we don't have a similar result for class 2 rats, but we have some results for specific types of class 2. For example, time fair, where if we have n users and m base stations, then we can actually bound this gap between centralized and distributed by 2 if there are more base stations than users, or this quantity m plus m divided by n if there are more users than base stations. And we'll actually show you some results to verify these on the next slide. So now that we've developed some bounds, let's talk about some simulations. Let's show some numbers. So what we did was we actually performed hundreds of measurements to obtain SNR values of multiple wireless access technologies in an indoor building, and we analyzed their performance in a realistic environment. So we obtained the information on the number of wireless towers, as well as the received SNR at the receiver, in addition to their frequency of operation and technology, at 100 randomly selected locations over AT&T's cellular network. In addition to these cellular statistics, we also measured at these same 100 locations the SNR of Wi-Fi base stations, frequency of operation, and technology. For example, 802.11a, b, or g. And basically, we created a database of 100 different users that we used for our simulations. So for our simulations, we randomly chose 9 users out of our database of 100 users, gave them access to 2 Wi-Fi and 1 3G rats based on their actual recorded measured values. And we ran these simulations over 20 trials. So in the graph on the right, you see the CDF of the Pareto efficiency gain for all of the Nash equilibria from these simulations. For throughput fair, which is class 1, time fair, which is class 2, and mixture, which is both of them. So what we saw, recall that for, on the previous slide, the first theorem stated that for class 1 models, this Pareto efficiency gain can become unbounded, and we exactly see that with the blue line at the very top trending all the way down. And for time fair, if you recall this equation down here, because there are more users, 9 users and 3 base stations, it falls under this second regime. And so it's bounded by about 12 divided by 9, which is 1 1/3, and you sort of see that with the red line. So next we also looked at the total equilibrium points in the system. So figure A shows the average number of equilibrium points in the entire system as a function of eta, our switching parameter. And again, recall that eta is describing how much throughput we need to achieve in order to switch. So if eta equals 2, that means we need to achieve at least twice the throughput on the new route to switch. And what's really interesting is the sheer the smallness of the number of equilibrium points for perfect switching, eta equals 1, where you switch as soon as you get a better throughput. In this case, throughput fair, we have 200 equilibrium points, time fair only 4, and mixture only 8. 8 states in 3 to the 9, which is about 19.5K equilibrium points. And what you can see here is as you increase eta, because as the switching threshold increases, you need more gain to switch, more and more points become equilibrium. In figure B, we see the average number of equilibrium points for the mixture model, which are these green bars, but we've split them up into equilibrium points that are Pareto-optimal and non-Pareto-optimal. And what's extremely interesting here is that as you increase eta, the relative ratio of Pareto to non-Pareto actually stays about the same, which tells us that we can increase eta and still preserve the average Pareto efficiency gain. Finally, we look at the steady state and transient behavior of rat selection games using our own distributed algorithm. So figure A explores the equilibrium distribution of users on Wi-Fi and 3G. So the way to read this graph is any point all the way on the left represents all users on 3G, and any point all the way on the right represents all users on Wi-Fi. So we ran this for 10, 30, and 50 users for 100 trials each. What you can see is clearly, in all three cases, more users prefer to associate with Wi-Fi. However, as you increase the number of users past 30, then more and more users start associating with 3G. This is due to saturation on Wi-Fi. And in figure B, we look at the average number of switching per user to get to convergence, basically the transient behavior. How many switches does it require per user to get to convergence? And we've been able to do this for M, which is a function of the number of rats, M, 2 on the left and 5 rats on the right, and the number of users, 10, 20, 50, and 10, 20, 50 for both cases. What we see is, as we increase the number of rats from 2 to 5, we actually don't get that much number of switchings in increase, maybe about 1. And by increasing the number of users, not much actually changes. And this is also seen in maximum convergence time. So the main takeaway from this is that because we can play around with eta, we can increase eta to decrease the convergence time. So we can use eta as a trade-off, basically trading off between how fast we converge and the overall desirability of our convergent points. So this work is actually far from finished, and there's a great number of directions in which this work can go. For example, we can look at how to make interface switching practical. For example, looking at switching delay, looking at energy cost and application interruption. We can also look at traffic offloading, for example, femtocell use for maybe not so mobile users. We can also look at simultaneous antenna use, for example, traffic splitting that we've so far not looked at in our current research. And again, we're currently involved with Intel Corporation and 3GPP in a standards effort. And this is the paper, the citation for Infocom. Thank you. Questions?